Need to capture server logs in your client application while keeping full control over how they're processed and routed. We'll show how FastMCP2's built-in log forwarding works through the MCP protocol's dedicated logging channel, automatically mapping server log levels to your client's logging system. Once the connection is initialized, you'll see how the Async context manager ensures proper connection cleanup, while still allowing custom log handlers for specialized processing, with all server-to-client logs also recorded in the server's context logger at debug level for full traceability.
Client equals client, my MCP server, hi. Async with client. Hash server logs are forwarded at their proper severity. Debug info warning error critical. Await client call tool, some tool.
This demonstrates the MCP protocol's built-in logging channel pattern, where server logs are forwarded to clients through a dedicated communication channel with preserved severity levels and structured metadata. The implementation uses an Async context manager for connection lifecycle while requiring explicit initialization, either automatically or via initialize, to establish the logging pipeline. The pattern is distinctive because it provides sensible defaults through the MCP protocol itself, while allowing full customization via the log handler parameter when specialized processing is needed. The approach works by establishing a dedicated logging channel over the transport layer during connection initialization, with logs flowing from server to client as structured LogMessage objects containing both content and metadata. While the Async context manager ensures proper resource cleanup, the actual log forwarding operates through the MCP protocol's built-in channel rather than a generic pub subsystem. Server-to-client logs are simultaneously recorded in the server's context logger at debug level, creating a dual logging pipeline that maintains visibility on both ends of the connection. This pattern addresses critical observability needs in distributed systems by providing real-time, severity-aware logging without requiring custom infrastructure. The balance between sensible defaults and customization via log handler makes it suitable for everything from simple debugging to complex production monitoring. The structured message format and dual logging ensure consistency across environments, while the explicit initialization requirement prevents accidental log leakage in improperly configured systems. The transport layer abstraction means the same pattern works whether using SDDIO, HTTP, or other transport mechanisms. Let's break it down line by line.
Client equals client, my MCP server, hi.
Initializes a client connection to the MCP server defined in my MCP server, Pi, using the MCP protocol's built-in logging channel for structured log forwarding. The connection requires initialization, automatic or via initialize, and forwards server logs with preserved severity levels while also writing them to FastMCP server context to client at debug level. Log forwarding works out of the box, but can be customized via the log handler parameter. And the Async context manager ensures proper connection lifecycle management, while the underlying transport layer, like SDDO transport, handles process communication.
Async with client.
Async context manager that handles connection lifecycle while enabling MCP protocol's built-in log forwarding. Logs stream from server to client at original severity levels, debug info warning error critical, via the protocol's dedicated logging channel, with messages including both content and metadata, provided the connection is initialized automatically or via initialize. Customization is supported through the log handler parameter, and server-to-client logs are also recorded in FastMCP server context to client at debug level.
Hash server logs are forwarded at their proper severity. Debug info warning error critical. Await client call tool, some tool.
This executes some tool while forwarding server logs through MCP's dedicated logging channel, preserving original severity levels and metadata. The Async context manager ensures proper connection cleanup, but log forwarding requires prior initialization, either automatic or via explicit initialize, and can be customized through the log handler parameter. Server-to-client logs also appear in the server's context logger at debug level, with all messages containing structured content and metadata per FastMCP's LogMessage type. The pattern leverages MCP's built-in transport layer, like SDDO transport, for process management and communication, supporting both default and custom logging configurations. FastMCP protocol logging. The Async context manager establishes the connection lifecycle, while the MCP protocol's dedicated logging channel handles bidirectional log forwarding, preserving full severity levels and structured metadata through the LogMessage type. Connection initialization must complete before logs flow, either automatically or via explicit initialize. Calls, with all server-to-client messages also logged to FastMCP server context to client at debug level. This pattern creates transparent observability while maintaining strict environment isolation. Server configuration requires explicit environment variables through the transport layer.
The connection that carries logs becomes the log it carries.